Okay, so for our today topics, we're gonna focus on how to model components of vibration system. If you still remember from the last class, we draw some free body diagram of a simple system that have the spring component, the inertia component, and the damping components. So today, mainly we're gonna try to model this component. If we have more than one spring part in the system, how can we obtain the equivalent stiffness of the spring? If we have multiple inertia part, the linear mass or the moment of inertia in the system, how can we combine them to be the equivalent mass of the system? And you know, for the spring, we may think about the mechanical spring that made from like spring steel, something like that, and it formed in the shape like coil spring. Today we will see how can we derive the stiffness of a coil spring from the material property of the spring. And many times we see the spring like the elastic beam like that. So we're gonna have a short review from the mechanics of material. How can we obtain the transverse stiffness, the deformable, the transverse deformation, the stiffness of the cantilever beam or the beam in different configuration of the support. And we're gonna review the idea of the static deflection before we consider the deformation of the spring in the initial state with the effect of the gravity. The spring already deformed in the initial state of the deformation. We are going to talk about the static deflection. And yes, when we have multiple springs in the system, when the springs are connected in series, in parallel, or in more complicated configuration, how can we obtain the equivalent stiffness of the system? And the elastic energy, the potential energy can be in the form of the elastic potential energy and gravitational potential energy. We're going to review two of these. And maybe before this, we may familiar with mass and spring system because we study it in the simple harmonic motion and it's gonna vibrate forever. But in this class, the new component that is quite new for you is the damper. When the force is depend on the velocity of motion. So today we're gonna see how it works, why the damper had this property, the property that the force is varying with the velocity of motion, and the inertia component. How can we obtain the equivalent mass of the system when we have more than one inertia component in the system? So for the equivalent stiffness, we can obtain from the summation of the spring, or we can consider by the potential energy that stored in each spring. The total energy that stored in each spring need to equal to the total energy that stored in the equivalent stiffness. For the viscous damping and for the inertia component, to obtain the equivalent damping coefficient and the equivalent mass of the system, we also use the same concept. We consider the energy that stored in each component for the all component need to be equal to the total energy of the system. And let's begin from the basic concept of the vibration system. If you see the simple diagram here, we can see the mass, the spring, and the damper. And the mass store kinetic energy. If the mass doesn't move, the kinetic energy gonna be 0. So the inertia component, the moment of inertia or the mass only have energy when it moves. How about the stiffness component? The spring that store the potential energy only have energy when it have deformation. Only when it have deformation. If the spring isn't deformed, if the spring have 0 deformation, the potential energy also 0. For the damper, if the system doesn't move, don't have velocity, the energy provided by the damper also 0. No, maybe this is not always true. Today, we will derive the energy that relate to the damping component. For the spring component, the energy stored in the spring can simply be written like this. But for the damper, the energy that dissipated by the damper, we need to obtain it from the integration. So we will see the detail today. And energy source to the system. Energy source to the system. Now, if the system begins from the equilibrium point, the free length of the spring, if it begins from delta x equal to 0, and we don't have any other additional force that apply to the system not gonna move. But the vibration system, the vibration system have motion because they have initial energy in the system. Initial energy may come from, we already have pre-extension of the spring, or initial velocity. Pre-extension means delta x when time equal to 0, not 0. Have initial velocity means the x dot when time equal to 0. It's not 0. If the system is moved away from the equilibrium point, it stores initial energy. It stores the potential energy of the spring. And during the time pass, it transforms the form of the potential energy to be the kinetic energy of the mass. And they're going to be the transform of the energy. If we have damper in the system, we're going to throw the energy out from the system. And finally, when the total energy of the system becomes zero, the motion will stop. So energy source of the system consists of two possible ways. The first way is we have the initial energy in the form of initial displacement or initial velocity. If the system don't have initial energy when time equal to zero, another possible way to make the system vibrate is to add the external force to the system. We may have a force that apply on the mass. The force as a function of time may be sinusoidal function or maybe just a step function. When time less than zero, the force may be zero. When time is more than zero, the magnitude of force may be equal to one value. Or we can have the different form of the force applied to the system. And in this class, we're gonna see if the input force is sinusoidal, if the input force is a kind of step function, or even maybe a lamp function. When the force increasing with time, how it's gonna affect the response of the system. So the input of the force to the system is straightforwardly, but the imposed motion, what does it mean by the imposed motion? Wait a second. Sorry,ครับ. Okay, continue. So the imposed motion may be if you have a wheel of an automobile, we have a spring, we have a damper to the wheel, and the wheel is traveling on a contour of the road, and the contour may be defined by y as a function of the displacement x. We're gonna have the imposed motion that apply to the system. But what I want to say is, finally, we can represent the imposed motion, the imposed displacement here, by its effect on the force that apply to the system. For example, if we know that this motion of the vehicle is varying with time, and we know that the contour of the road is a function of the horizontal position, and we know that the horizontal position is also the function of time. So it means that you can find the function of y as a function of time. You can find that how the y change against the time. So the y can change against the time, and the mass of the car also move against time. It don't need to be fixed. Sometimes when the car run on the top of the bump, we may have the y increase. Sometimes when the car travel on the bottom of the bump, maybe the value of the y1 also decrease. But what we need to know is the distance between the y and y1 don't need to be a constant if the spring can be formed, if the damper can be formed. If we just draw the free body diagram of the mass, we have the spring force that depend on the difference between y1 and y. And we have the damper force, which is the function of the difference between the velocity of y1 and y. So the input of the system or the energy source can come from the initial before the system begin vibrate, or can be the input during the vibration. And the spring is the flexible mechanical link between two particles in the system. If we come back to this picture, as I mentioned, if we have a rigid suspension, y1 and y always constant. But when we have a spring here, we can have a deformation. So y, or the height of the mass from a datum, don't need to have a constant difference with y when we have the deformation. So spring is a flexible thing that connect between two particles in the system. And many times when we have the picture like this, and we just draw the spring to have the spring force to the right hand side and to the left hand side. This only true when the spring is neglected in a shear. We can say F equal to K delta X when delta X is the deformation. Only when we neglect the inertia or the mass of the spring. On the right hand side, on the left hand side, if the spring have the mass, we need to consider the mass of the spring and the acceleration of the center of mass of the spring. And we're gonna have the difference between the force on the right and on the left hand side of the spring. And unstretched length of the spring means the length of the spring when we not apply the force and linear spring by the hook laws. Linear spring by the hook laws is just an approximation from the actual spring. Actually, the hook law is come from experiment, but to explain why F equal to K delta X, we may begin from the general polynomial form. Before we conduct the experiment, we only have the hypothesis that the force need to be a function of the displacement or the deformation of the spring. The function can be the general form of polynomial function, or the 1, 2, 3. But what we know is that when we don't have the deformation of the spring, we have zero force. When we don't have the deformation of the spring, we have zero force. So K0 should be 0, right? Because when X equal to 0, the force also 0. So K0 need to be 0. Another property is when we have a spring, when we pull it to the positive X, the force generated by the spring will be to the left-hand side, right? But when we try to push the spring to the left-hand side and displacement is less than 0, the force generated by the spring will be to the right-hand side. When we try to compress the spring, the force will be on the opposite direction. So when we have the same magnitude of displacement but opposite direction, what we can get is we have the same magnitude of force but on the opposite direction. It means that the spring needs to be the odd function. The second power, the fourth power gonna be removed. We only have the odd power in the function. The last assumption here is with the small deformation of the spring, the higher power of the deformation are neglected. If we consider the spring with bigger deformation, of course, we may see the clear difference between the hook laws when it adds the effect of the higher degree of the polynomial in the odd degree. But with the small deformation, we're gonna assume the spring force with a constant K to make the force varying against the displacement, and the K of the spring is the tangent of the slope when x equal to 0, the initial slope when x equal to 0. So here is where how to explain why we only have the first degree of the displacement from the Hooke's law. Potential energy function of spring. We need to be careful here that the work here is done by the spring, not the external force. So when we compute the work done by the spring, if we apply force, to the right hand side, with the positive x direction, the spring force gonna be minus k with the x. If x is negative, the force gonna be to the right hand side. So the force always be minus kx. If x is positive, F generated by the spring will be in the negative direction. If x is negative, minus, we're gonna have the force to the right hand side. So when we pull the system to move from the initial state to the final state, when we move from the initial state to the final state with x displacement, of course, the work done by the external force may be positive mechanical work, but the work done by the spring is the integral of the spring force that have the opposite direction with the displacement, and integral from the initial to the final state. So the integration here gonna be minus k and x squared divided by 2. Limit of integration from x1 to x2. Right? So we're gonna have minus k x2 squared divided by 2 minus kx1 squared divided by 2. And the potential energy function is defined. The mechanical work that done by the spring force from the initial to the final position is the difference between the potential energy of the initial function subtract by the final function. And at each position, we only consider the x at that state, and we define the potential energy function as that current deformation. Here is for the linear spring. If we talk about torsion spring, if we talk about torsion spring, we have the moment. The linear spring, we have F equal to K X. Actually, X should be the delta X, but we always set X0 equal to 0 at the unstretched length of the spring. For the torsional application, we have the moment as a function of the delta of the theta. When we have a bigger torsion angle, we have bigger torque, and the potential energy function for the torsional application is also similar to for linear application. We have torsional stiffness, and we have the angular displacement. Here, when we try to provide the longitudinal force, it gonna create the longitudinal displacement and vibration. How can we obtain the Hooke's laws for the longitudinal vibration or the longitudinal spring? We may need to come back to the definition of the Young modulus. Definition of the Young modulus. Do you still remember the Young modulus? It's equal to the stress divided by the strain. The stress is the force divided by the cross-sectional area of the component. The strain is the deformation divided by the total length before we apply the force. So when we try to rearrange the equation so that we find the relationship between the force and the displacement, we're gonna have force equal to the Young modulus multiplied by the area and multiplied by delta X per L. So the stiffness, the spring stiffness for the longitudinal vibration, for the elongation of a beam, the stiffness is a function of the Young modulus the cross-sectional area and the length. If we have the same material, if we buy it from a store, one material have a constant Young modulus and may have a constant cross-sectional area. Do you have any idea if we want to have a higher stiffness? If we want high K, do you think we should cut the spring to be short or long so that we can have the high stiffness?
Short, right?
Yes, correct. So if we have a short material, it's difficult to extend it. If it's long and it have the same Young modulus, same area, it's easy to have the delta X with the same magnitude of force. And how about the transverse displacement? The most simple one is a cantilever beam that we apply force and we can see the displacement. We apply force and we can see the displacement. Maybe you need to review what you learned from the mechanics of material. The stiffness for the transverse displacement with the cantilever beam. Cantilever beam means the support not only fix the translation here, not only fix the translation, but it also generate the moment to make this slope to be 90 degrees. Here is the cantilever beam. The mid-span pin beam. The meaning is you have the pin and you have beam. So we apply the force and we can see the delta X. For the pin, the pin support, maybe this is not a good picture. Sorry. Okay, this should be better. The pin support only guarantee the displacement at the support position. The displacement gonna be 0, but the slope dy by okay, we may have force and delta y, and the horizontal position may be x. For the pin support, y equal to 0, but the dy by dx when y equal to 0 don't need to be 0. For the pin support, when x equal to 0 and x equal to L, I'm sorry, again. Consider this picture. We have y for the vertical displacement. We have x that indicate the position of the element on the beam. X equal to 0 means at the left pin support, if the bar have the length L, on the right pin support, X equal to L. For the pin-pin beam, Y, when X equal to 0, it's 0. We don't have displacement. Y, when X equal to L, also 0, because we don't have displacement, vertical displacement. But the slope dy by dx, when x equal to 0, the slope here don't need to be 0. But for the cantilever beam, the slope will be 0. Because the pin support only can create the force to prevent the motion, but it cannot generate the moment to prevent the rotation about the pin. For the fixed beam, we have one side as a cantilever and another side also fixed. For the fixed beam, we need to have 0 slope on both ends of the beam. When we not focus on equation, just only use our engineering sense, when we're not talking about the equation, just use our engineering sense. For the fixed, we apply force to get the displacement delta y. For the pin, we apply force to get the displacement delta y. Do you think in which case we should have higher stiffness? K, higher. Pin, case A. Fixed, case B. Which one? We should have higher K. Okay, thank you, Kantiti. Kantiti answer that maybe fixed, we're gonna have higher stiffness. It makes sense because if we don't allow the beam to have a slope here, we're gonna have a small deformation. If we can allow the spring to have the non-zero slope at the support, it's more flexible. We can have bigger delta y for the pin case. When we can have bigger y with the same magnitude of force, it means pin can generate lower stiffness compared to the case of the fixed. So if you review the mechanics of material, yeah, we can see this. And how about the torsional application? Here is the torsional stiffness. The moment have the torsional stiffness multiplied by the angular displacement. But how can we obtain this? We may need to begin from the definition of the shear modulus shear modulus is the shear stress divided by the strain, the shear strain. If we see the cross section of the if we see the cross section of the rod, we can bend it torsion by the theta angle, and the element on the surface of the rod will have the max shear stress. The max shear stress on the surface of the rod is the magnitude of the torque, or maybe to prevent confusion with the tau, the moment that we apply. The diameter and the tool of the second moment of area, the shear stress is equal to the moment that we apply multiplied by the diameter of the rod divided by 2 of J. J is the second moment of area. How can we obtain J for the circular rod? The circular rod. Maybe actually J is equal to the integral of r squared dA. The radius and the area from r equal to 0 to the full radius r. For a circle, the second moment of area may be the integral from r equal to 0 to r equal to the radius and r squared. The dA, or the small area against the change of the radius, may be composed from the area of this ring. The ring has the length, total length 2 pi r, and the ring has the width of dr. So the area dA against the change of the radius r may be composed from 2 pi r dr. So how can we obtain this integral? We have 2 pi and integral of r power 3 dr from 0 to r, right? 2 pi of r power 4 per 4 of 0 to r, and it's gonna be pi per 2 of r power 4. Here, the second moment of area is written in the form of the radius of the rod, to make it correspond to the formula of the tau. Try to change it to be the diameter. Radius is diameter per 2, right? So the total gonna be pi per d power 4. And what next? Now we have the tau and we have the j, we have the moment, we have the diameter. So I think now we cover the maximum shear stress, but what should be the strain? How can we explain the shear strain of the rod? You need to consider this rod as a cylinder. You need to consider the rod as a cylinder. And maybe in the beginning, the rod is not subject to the torque. It don't have the deformation. But when the rod deform, on this side we fix the point on the surface of the rod, point in the vertical line. When we don't have the moment, we have this vertical line. But when it's subject to the moment, the rod deform, and on another end of the rod, the point on the surface deviate by the angle theta, The strain here is defined by the if we draw an angle, if the strain is defined, if we draw a triangle, and this side of the triangle is the length, the shear strength is the angle that composed from this displacement and the length of the cylinder. And this displacement, we obtain it from the angular displacement delta theta multiplied by the radius of the rod. The rod has the diameter d. This distance is the angle multiplied by the radius of the cylinder. The angle of deformation delta theta at the position far away from the center, of the cylinder, center line. The distance d per 2, diameter divided by 2, and angle about the center line is delta theta. So now the shear strain, is equal to the delta theta d per 2 and divide by length of the rod. So can we find the relationship? We come back to this equation. The G is equal to the shear stress. Shear stress is this one, MD per 2J. But J is this one. J is 32 divided by pi d power 4. And we divide by the shear strain. Shear strain is L, 2L, because we have 2 here, and D, and what next? Wait. Delta theta. So we have D cancel, 2 cancel, and we have the delta theta here. We have the moment, and we have the terms for the length, and wow, I'm sorry, here they didn't derive the J. They leave it in the form of the J. In this case, it's more simple than what we are going to do. Maybe in this case, the rod don't need to be the circular cross section. It may be a square, or it can be a circular cross section with a hollow inside. We need to review how to obtain J for the different cross section, But for this, we give an example when cross section is a complete circle. If we only want to leave it in the terms of J, actually it's more easy. G is equal to the tau. Tau is MD per 2J, right? Tau is MD per 2J. And the strain is equal to delta theta D per 2L. So divide by the strain means multiply by 2L per delta theta D. So 2 will cancel. and D will cancel. Finally, we can write the moment equal to G multiplied by J and divided by L delta theta. Okay, so if we need to obtain the torsional stiffness of a rod, maybe a circular rod, a square rod, we need to know the second moment of area. We need to know the second moment of area and the shear modulus and the length of the rod. Again, I'm gonna repeat my question. Do you think if we have long or short rod, we're gonna have higher angular stiffness?
Short.
Yes. If you try to bend, no, if you try to twist a deformable shaft, if the shaft is short, you cannot create angular displacement. But if the shaft is long, maybe you use the same amount of the torque, you can create the angular displacement on that deformable shaft. So when you design the system, if possible, we may prefer a shortest possible length of the shaft so that we can avoid the effect of undesired deformation in the structure.
I'm sorry. When you derive J, why we have to integrate R square?
It's the definition of the second moment of area. Actually, it's the definition of the J. I'm not sure if you still remember the moment of inertia. In the physics class, if you still remember, moment of inertia is equal to integral R square dm. Do you familiar with something like this?
Yes. Okay.
Moment of inertia, integral R square dm. But for the moment of inertia, we need to consider the density of the things and multiply by the area. But for the case of the second moment of area, we're not talking about the mass property, the density. We only consider the effect of the area distribution in the cross section. So why we have R square? It comes from the definition of the second moment of area.
Okay, thank you, sir.
Yes. And this is gonna be the most complicated one that we extend from the previous derivation. Please don't be like sleepy, okay? This is gonna be the last boring slide for today. Beginning from the next slide, it's not gonna be boring like this anymore. This is gonna be the most boring one. So before this, we talk about the shear stress, the shear modulus. But if we have a coil spring, and we apply the force, how can we derive F equal to Kx for the coil spring? So the idea is we consider only one revolution of coil. We consider only one revolution of coil. In this one revolution of coil, the force, the linear force, is transferred from coil to coil along the center line. The force is transferred from coil to coil along the center line. And the cross section of the coil in this case is circular cross section of the spring coil. Many times we may see the spring coil has like rectangle cross section. Many times we may see, well, I'm not good at drawing the things. Yeah, many times we see the spring coil have the rectangle cross section, but in this case, the cross section is circular cross section. The coil has the radius r. The coil has the radius r. The rod has diameter d. The rod has diameter d. So if we make it to deform, by the force F, if we make it to deform by the force F, what's gonna change is by applying the force, it seems like we are going to create the shear deformation about the center line of the rod. We are going to create this angle delta theta. We are going to create delta theta. If we try to pull the spring coil with the force F, and the force F is made on the center line of the coil with the distance r or the coil radius, it seems like we are going to generate the shear deformation from the center of the rod, We come back to the shear, the maximum shear stress equal to maximum shear stress equal to the moment multiplied by the diameter per 2J. Here is the rod, steel rod that we make it to be the shape of a coil spring. If we try to extend the rod to see it as a cylinder, now we have a cylinder rod, but we make it to be a coil spring. And for one revolution, the length of the rod gonna be 2 pi r. For one revolution of coil, the length of the rod gonna be 2 pi r, when r is the radius of the coil. If the total number of coil 1, 1 coil, 2 coil, 3 until n. If we have n number of coil, the total length of the rod may be n coil multiplied by 2 pi r. So n number of coil, r is coil radius, and we create the shear deformation. We create the shear deformation. We try to twist the rod to create shear deformation. The same picture. In the beginning, on the surface of the rod, we have a reference point here. If the rod is not subject to a twist, if we don't apply any torque to twist the rod, the reference position, oh, I'm sorry. I should draw it like this. Okay, like this, better. If we not twist the rod, the reference position, the mark on the surface should remain the same. But what's gonna happen if we try to twist the rod with moment? The marker will change the position in the direction of the moment. And if we draw a line from the first reference point to here, I hope you still remember the angle here. What is this one? What is this one? The angle before it twists, the angle is the shear strain. Shear strain is the angle that compute from the length of the rod and the distance, the deformable distance here. So what should be this distance? What should be the distance? If we know that the total angle in one coil, it may have delta theta, but the spring has n coil. So actually the total angle should be n of delta theta. But in this case, what I'm going to write is the delta of the theta is the total angular deformation for all the total coil for n coil. For one coil, it may be d theta, but for n coil, the total deformation will be delta of the theta, and the coil itself has the diameter d. Do you have any idea about this distance? It needs to be delta theta multiplied by the radius of the rod. The radius of the rod is the diameter of the rod divided by 2. Diameter of the rod divided by 2. So what we have now, we have the shear stress and the shear strain. The shear strain is this one divided by L. Shear strain delta theta multiplied by rod radius, delta theta multiplied by the rod radius divided by the total length of the rod. The total length of the rod comes from the number of coils multiplied by one revolution length of the coil. The number of coils and one revolution length of the coil is 2 pi r. When r is the coil radius, d is the rod diameter. For a circular rod, we derive J from the integral r square dA from r equal to 0 to r equal to the radius, and we already derived J from here. Integral r square dA from r equal to 0 to r equal to the radius. And for a circular cross section, the second moment of area will be pi d power 4. Pi d power 4 per 32. So what I'm going to say is the shear modulus is equal to the shear stress divided by the shear strain. The shear stress divided by the shear strain. So the stress is moment multiplied by d and divided by 2j. One missing thing is, do you have any idea about the moment? Do you have any idea about the moment that twists the coil from the given information? Do we have any idea about the moment? We know that the force, the linear force that apply on the coil is F, and the coil has the radius R. The coil has the radius R. So the moment that we apply about the center line of the rod gonna be force multiplied by the distance that measure from the center of the rod to the force, and this distance is the radius of the coil. So M is equal to the force multiplied by the radius of the coil. So from this, shear modulus is equal to the tau md per 2j. M, or the moment, is the force multiplied by the radius of the coil. D is the diameter of the rod. 2J. J is 32 divided by pi d power 4 md per 2J. Moment D per 2 and J. And the strain as a denominator gonna be number of coil, 1 revolution length of the coil, and the delta theta. Wow, I missed one last thing, but let's leave it. The delta theta and D and 2. The last thing that I forgot to do is how can we relate the delta theta to the linear displacement? How can we relate the delta theta to the linear displacement? The delta theta is the angular displacement at the center of the rod. If we want to transform it to the delta x, the delta x need to be measured at the center line of the spring. The delta x need to be measured at the center line of the spring. The delta theta, when we multiply by the coil radius, it will be the linear displacement of the spring, delta x. So delta x, delta theta is equal to delta x divided by r, delta x divided by r. So please check by yourself to finalize this. What we want is how can we form F equal to K delta X. Now we have force here. We have delta X. And the rest of the things in the equation, the shear modulus, the radius of the coil, the diameter of the rod, the number of coil, the rest of the things in the equation are constant. And when we switch the sign of the equation, rearrange the equation, finally we can obtain K in the terms of shear modulus, radius of coil, diameter of the rod, number of coil. And when you already derive this, try to think that if it makes sense, hey, if we increase the number of the coil, how can it affect the stiffness? Hey, if we increase the shear modulus of the material, how it affects the stiffness? Hey, if we increase or decrease the diameter of the rod, that is the spring material, how can it affect the stiffness of the spring? Okay, before we continue with thing that non-boring anymore, let's have a 10-minute break. So see you again at, so I will leave it on this slide and see you again at 2:40. Have 10-minute break.